Okay, so to get started, somebody had a question about doubling time. And we remember, as they point out in the question, that there's a way to calculate it for exponential growth and a way to calculate it for geometric growth. So why don't we go ahead and find that module. So just briefly, share my screen on my notes. So this is what I found about doubling time. So the basic definition is just the time required for a population to double in abundance. And then these are the two equations. This is with exponential growth, and then this is with geometric growth, right? And in order to use these equations, you're going to have to be given some part of the information. You're going to have to be given the starting number of the population. You're probably going to be given the growth rate, and then the time that it would take to do that. And then you're going to have to be able to plug that in. So if you're talking about calculators, this may be a good instance where you might have to have a calculator that has the natural log or the e function, that you can raise it to the e here, or have the log function here.
So for that one, if we're trying to solve that, are we using the n equation or the t equals 1?
That would, what do you mean? Like this equation,
yeah,
part down here,
or the top one,
or the top one up here? I mean, this is the base equation.
Okay.
So it's gonna depend on what kind of information you were to be given.
Okay.
So if they gave you like this side of the equation, you could plug in n of t over here. But if they gave you other parts of the equation, maybe you're missing, you could use this part of the equation. This just simplifies it a little bit to solve for n. So what is the population number, or what is the time taken to double? So you could be asked either way to calculate it. So if you're asked how much time would it take for the population to double, you would use this equation on the bottom. And if you're asked what is the given the current population, the growth rate, and the time, what would be the doubling value?
Okay, thank you.
Yeah. And for this, I would say focus more on the concepts of doubling time. You're not going to be asked to calculate the doubling of a population, but you might be asked some questions about doubling time. Did anybody have any specific examples? Some people last night mentioned that they wanted to go over some calculations again. Okay, so from the chat, there's a question. When would we use the geometric equation versus when would we use the exponential equation in terms of concepts? So they might ask you, remember some of the activities asked you about some of the assumptions of the equations. So they might ask you which equation or which model has a certain assumption. That's what I'm trying to get at with concepts, where it's not going to be a mathematical calculation, but it'll ask you something. What does this model assume, or when would be most appropriate to use this model? Why is this model correct and why are the other choices wrong? That could be a question. So knowing what the models all take into consideration is going to be important. Because in the chat, what do you mean by going over population density when it comes to density dependence? So if the population starts at a high or low number?
No, I think I just mean, like, I understand the concept, but I think I get population growth and population density like confused. Like, I know population grows as the population grows, but it says like, oh, population growth increases while population density increases. It just like population density is just the amount of organisms in one place.
Yeah, so population
Okay.
density could be also called population number,
Okay, thank you.
or the number of individuals in that given population.
Got you. Thank you.
Yeah, and then population growth, as you said, is just how many more individuals go into that from that population from birthing rates.
Yes. Okay, thank you.
Yeah, so for the chat, they asked to confirm you'll be given lambda. Yeah, you'll be given the equation, and you could in some instances be given lambda, or you could be given everything else and asked to solve for lambda. But you're not going to have to like calculate anything out of thin air. If that, I mean, you're not going to have to remember the value or something. You'll have to have some numbers given to you to be able to calculate a missing value throughout all the equations. Sure, so somebody wants to go over the survivorship curves. Let me find those again. So I think we can visually look at those. All right, well, let me share screen. All right, so we have this is the visual representation of the survivorship curve, right? And the difference is it's going to be the steepness of the curve and where the steepness occurs. So we have age on the x-axis, so how young on the left, older on the right, and then survivorship on the y-axis. And the higher up it is, the higher the survivorship. So if we look at this just as a figure, where is the highest survivorship for a type 1 organism in relation to age? Yeah, young, right? So they have low mortality or high survivorship. You can say it either way when they're young, and then it drops off when they get older. And a type 2, it's pretty stable, right? They have a pretty constant survivorship that decreases, at least the rate of survivorship is constant, but it decreases as they age. And then in a type 3, you're going to have a high probability of death or low survivorship that levels off as they age. So a lot of young will die in a type 3 rapidly, but then there'll be the ones that survive will make it to a fairly high age. And then it gives you some examples of animals or organisms that are type 1, type 2, and type 3. And why do we think of, what are some characteristics of a bear is the example they give us that would lead to high survivorship of their offspring at a young age?
Because they give off a higher parental care.
Yeah, so if they have high parental care is one aspect. As somebody said, lower numbers of predators. Yeah, they tend to be larger animals or larger organisms. Do they also think about birth? Do they give birth to 20 bears, 100 bears, 2 bears?
Their brood size is pretty small. It's like what, up to like maybe 3 or 4. So there's not that many children to take care of at one time.
Yeah, so they put a lot of energy into a fewer number of individuals. And they're able to also provide higher levels of parental care, as we said, because of that. And type 2 is a little bit different than that. The example here is a squirrel. They tend to have a few more offspring. They're smaller, so that we relate it to predators. They're more likely to get hit by a predator. And parental care is, they have some parental care, but it's not as long as in a type 1 organism. And a type 3 is the complete opposite then of a type 1. We think of insects or plants where they have hundreds or thousands of offspring because several of them are going to die or not make it very far. So they kind of, have a lot in hopes that some make it, and the ones that do tend to make it pretty far in age as well, or pretty far in age then. So are there any specific questions or anything confusing of what the difference between type 1, 2, and 3 are? The key thing is just knowing, do they have high or low survival early in life? That'll kind of, you might have a compare and contrast question talking about the survivorship curves. So that, big picture, that's definitely what you would be expected to remember and how to differentiate the three.
So hypothetically, let's say this question is on the short answer, any of the short answers. Do you know if they're going to be asking for specific examples? Like, I think in previous short answers, they were like, oh, and then compare it to a population of species that and how it also applied to whatever the question was. Is that going to continue into this exam too?
You're talking like the life history traits that we're kind of talking about?
Yes, just like in general, like, yeah. So like if for this question, like it'd be like, oh, type 1, like compare the difference between the 3 types, and then be like, oh, well, can you give us an example of a species that is in each category? Is that also going to be kind of included?
I would say if that would be in the short answer, the question would specify, give an example of an organism and some characteristics to describe it. So it would ask for those details.
Okay.
And then in a matching or a multiple choice or true false, it might ask something along the lines of, here's an example animal, which survivorship curve would best represent that animal? And if it was, that would turn into a short answer, you could have that question and say, why would that best represent this organism? And that would be the life history traits then. In general, I would agree with that statement that smaller animals tend to be type 2, larger animals type 1, and plants or insects type 3. I'm sure if we searched hard enough, we could find some exceptions, but I appreciate the word generally there, because a lot of the patterns we see in biology and ecology are general patterns. So. Sure. So someone asked if we could go over stochastic events and models. So why don't we just start off with the basic, what is a stochastic event? Yeah, so a random event. What would be an example of a stochastic random event? Yeah, so types of natural disasters, right? So maybe a tornado, tsunami, flooding, fire, any of those kind of natural disasters. And then what Cogbooks talked about is they tried to link how these random events or stochastic events could cause populations to go extinct. So what would make a population vulnerable? What about the population itself could make it vulnerable to these stochastic events? Yeah, if the population is small, if there's only a few individuals, there's less that have to get wiped out in order for them to possibly go extinct. What else about a population can make it vulnerable? Yeah, again, if it's isolated, so think about location, right? If they're all in one forest and that forest has a severe flood or a severe fire, odds are you're going to push that population to extinction. But if that population is maybe spread out into different forest patches and only part of the population gets hit by the fire, but part of it doesn't, that population that didn't get hit can continue to rebound and grow. and has a less of a possibility of becoming extinct. So then there were a few, there's a stochastic model. Then that one, we talked about random events. So obviously it's a model that incorporates random variation in population growth rates. What is the other type of model that Cogbooks talked about in relation to a stochastic model? Well, I talked about demographic stochasticity, but there was a simpler model than a stochastic model. Remember the deterministic model? So that's a model that's designed to predict a result without accounting for random variation. So a stochastic model could be more realistic if you expect random events to occur, but if you have an environment that is very consistent and doesn't have a lot of natural disasters, it might be better to use a deterministic model. But if we want to go back now to the deterministic, or sorry, what was it? Demographic stochasticity. Does somebody remember what that is? How it relates to random variation? Yeah, so we talk about demographic stochasticity. We're talking about when the random variation in birth rates and death rates is due to differences among individuals and not due to changes in the environment. So that's focused on the individual rather than the environment itself. Because then the next step would be, you could talk about environmental stochasticity, right? And that's when the random variation in birth and death rates is due to changes in the environmental conditions. So changes in weather or natural disasters. All right. Are there any questions about this, or anybody have additional questions, or? So deterministic model, again, just to rehash, that's the simplest model. So it's just a model that's designed to predict a result without accounting for random variation. And that could be a result in population growth or population decline. And the random variation could be either the demographic about the organisms or about the environment themselves. So it assumes that all the organisms are the same and that the environment is constant. So there is one kind of way of thinking that I want to make a little more clear for the group. So I made a couple of practice questions if we want to maybe go over those as a group. This will be about calculations. Okay, so everybody can see this Excel sheet, right? Okay, so you might get a question that'll give you a life table with some information. So here we're given the age, we're given S of X, and we're given B of X, right? So we're given, let's remind ourselves, what is S of X and what is B of X?
S of X is the survival range, whereas B sub of X is the birth rate or the fecundity.
Yes. Yeah, this would, Cogbooks often refers to S of X or S sub X as survival rate, or from 1 year to the next year, from like age 1 to 2 or 2 to 3, that single step. And then B of X, it correctly was said, is the fecundity or birth rate of that given age class. And then in the question, it's asking, what is the survivorship of an individual from birth to the age of 3 years? And what do we typically think of when we say survivorship from birth to a certain age? Yeah, L sub X, right? But you're not given L sub X in this scenario. How do you solve for it given these 3 columns? Is there an equation that we could use? So we know we want this, right? Do we know any values of L sub X that are always constant?
Would it be the age?
Not the age. No, somebody said L sub 0 equals 1. Yes, that's exactly what I was looking for. We know that that value is always going to be 1 because it's the number that survived in the population, right? So the first thing I would do on my scratch paper is I would make a new column and I would start filling it in, and we know that this is 1. So now we have an LX value. And you remember this equation? The L2 equals S1 times L1. So now, because this is how we know that LX is 1, right? Survivorship in the first age class is always set to 1 because all individuals in the population are initially alive. So using this equation, and something I want to clarify here is that the numbers are kind of weird how Cogbooks does this. It does, the ones are just, think of them in terms of age bracket. So it's the first age bracket. So here the S1 and L1 are going to be associated with age 0, because Cogbooks in this example made it kind of neat, but this could be 3 months, 6 months, 9 months, 12 months, or this could be 2 days, 10 days, and so on. It's not important that these are whole numbers or what the values are. It's just important to know which values they are associated with in the equation. So S1 is going to be the top value and L2 is going to be this value. So now we want to fill in this column, right? So how do we solve to get L2? That equals S1 times L1. So that's just, we have S1 is 0.6 and we know L1 is 1. So if we do equals 0.6 times 1, we know that L2 is going to be 0.6. And we can do the same thing for the rest of the equations where we just plug in, now we solve for, where is it, 0.6. So we had L2, but now we need to solve for L3, and that's just going to be using S2 and L2. So that just equals, I can click on it. That's just going to be our second value, right? So the 0.5 times our previous value we just calculated being 0.6 to give us 0.3. And then we do the same thing here where we do L4 is S4 times L3, or S3 times L3, sorry. So we do the 0.9 and we multiply that by a previous value. And then the answer is we're in year 3. So we got to pay attention of what the, the numbers. So year 3, the survivorship would be 0.27. Does that make sense how we got to that answer? Okay, because you are going to get like questions where you're not going to get the entire life table and get to pick just a number out of it. You're going to have to add columns, 1 or 2 columns maybe, and do some calculations to figure out some of these answers. So they will, in some instances, you will get to pick out the value. Some instances you'll have to calculate. So you got to just know what the question is looking for. What if we expanded this question then? Maybe this was a multi-part of a short answer, and I asked, what is the net reproductive rate? Do you remember how we calculate that? Yeah, so I already did it, where we solve for LX, right, in the previous step. Now what we can do is we can just add another column and get LX times BX, and that's just multiplying these values together and then summing them together, right? So we get a value of 3 point something, and then what that value means is that's the total number of offspring that we can expect an average female to produce over the course of her life. So if we have a value of 3 here, and we get asked this question, do we expect this population to increase or decrease, and why? What would we say? Exactly, from the chat, somebody said it would increase because the value that we got for the net reproductive rate is above 1. So this female is more than replacing herself. On average, all the females are going to be doing that in this population. So it's going to be growing. Yeah, so that, great. I mean, that was a good job. Everybody seemed to follow along. Are there any questions about these calculations that we did just now or what they mean? If not, I've got one more that I think might be worthwhile going through. So given this life table where we're given age, L sub x, B sub x, and then the L sub x times B sub x to us. And then the question here is which value equals the annual survival rate. So it tells us that we're looking for S of x of 4-year-olds. So again, now we need to solve for S sub x, right? So we have this column that we need to fill in. How would we go about doing this? Is there a way to know what the first S sub x is or no? No, the nx plus 1, that's the idea, but it's not the equation that I'm looking for here. And then to answer my question is no, there's no way to know S sub x. But what about the equation that we just used? Can we use this equation? Because now we have all the LXs. We have L2 and L1, right? That's L1 and that's L2. And we want to solve for S1. So we just do the same thing, but in a different way. So now what we're going to do is we can plug in, we know L2 equals S1, L1. And if we plug the numbers in for the first one, that's L2 is 0.6 and S1, we don't know, but we do know that L1 is 1. And what we can do is we can solve for S1 by dividing 0.6 by 1. And then that gets us a value of 0.6, right? So we just would do equals L2 divided by L1, and that's 0.6. We would do the same thing for finding S2, right? Because now we know what S1 is. We can plug that into the equation and we can solve for S2 because we know what L3 and L2 are, and we know what L4 and L3 are, L5 and L4, L6 and L5. So it's just the same equation, right? Where we divide them. And then we need to know, when to stop, right? So we got to go back to the question, and it asks us annual survival rate of 4-year-olds. So that's age 4. That would be this value right here at 0.5. And from the chat, yeah, we're doing the L2 equals L1 S1 equation to solve for S1. And then you can take it to the next step. Once you have S1, you can solve, well, you don't need S1 to solve. You can then solve for S2, S3, S4, and S5, and then just know which one of these values is associated with the question. Does that make sense how we did these calculations? Okay, so I think those are two examples where you're gonna have to add a column, possibly add a second column and do calculations and asking for values that are not in the current table, but you need to build and fill in the rest of the life table. Trying to look at my notes where we would pull the nx plus 1 possibly. I don't know if I'm thinking that's exponential growth. Okay. Oh, I think those have to do with if you want to calculate how many individuals are surviving or how many individuals are dying per age class. Yeah, so that would be more, I think it was related to this activity. Let me share my screen again. So in this activity, you were given a matrix table. You were given the number of individuals in each age bracket, and you were given the fecundity, the BX and the SX in the matrix table here, right? And then this is where the T plus 1 comes into case. So you know the ages, you know the birth rates, that's the top row, and you know the survival rates associated with each age, because that's the diagonal right here, right? And then if I ask you maybe how to calculate births or how many new babies per age bracket, or how many survive each age bracket or how many die. Yeah, knowing this is going to be important too. So then to fill in this table, this is where that equation birth is this, you take the number of individuals and you multiply it by the birth rate. And then because the birth rate for the first two age brackets is 0, both of those values are going to be 0. But for 2-year-olds, it's going to be 7 new babies, 3-year-olds, 10, and 4-year-olds, 12. And then if you want to know the total births, we know that that would be, or T plus 1 would be, if we round it, it'd be 40 individuals in that next generation. And then survival is the same idea. How many of the original 122 newborns are going to survive to be 1-year-olds? So that's just the number for that age bracket. So n sub 0 is 122. And we multiply that by S of x, the survival rate, and we have 115 surviving. Here we have 99. And then we can add up, you know, the next year's population is going to be 283 surviving plus the 39.6 that were born. Yeah, what you would be given is you would be given this matrix table right here. So you'll be given the age brackets, the number per each age bracket. You'll be given the fecundity rates and the survival rates. You just have to know how to recognize what these numbers mean. is then some of the questions I think from the activity is it asks us how many 3-year-olds would you expect in the population at T+1 from that matrix table? And then you would have to be able to know where these numbers come from, right? So this is how many 2-year-olds survive from our table. If we look at 2-year-olds, we had 35, they had a survival rate of 98%, and we had 34.4 or 34 whole individuals survive. So that's how you would answer that question. And I recommend building this table on so you can go back to it. You're not going to use all the values necessarily, but you don't know which ones you're going to use. So I think it's, doesn't take terribly long to calculate them all out, and then you can just reference the table. Are there any questions about how we built this table or what goes into it?
Just, it might be a stupid question, but when you're answering, like, okay, so you age and birth rate, when we come up with the survival in adults, where it's like, oh, 34.44, like if we have to answer, do we just say 34.44 adults would survive, or?
If you put that down, that would be okay. I would say round it to the whole number because we're talking about whole organisms.
Thank you.
So in this instance, I would say 34. In this instance, if you said 25 or 26, I think you could argue it either way. You say I round it up to 26, or I just chose the first whole organism because you can't have 0.6 organisms.
Got you. Thank you. That's what I was trying to
And if it's multiple choice, just pick the one that best associates. So I think the multiple choice was 34 was one of the possible answers in this activity. So you would just, it was 34.4 was the math, but you picked 34 because that's the closest answer to what you calculated.
Mm-hmm.
And if there is some weird thing on the exam I overlooked where it's 34 or 35 and you picked 35 because it was 34.6, I would give you full credit back if you came back and said, I did it for these reasons and this was the choices. And then I made an announcement where I posted this YouTube video, which goes into a little bit more detail about how to make these specific tables, how to calculate new births, survival. And I think the example goes through more than one generation too. So it shows you how to build like multiple tables of these. And I think it does a really good job of laying it out and writing out the calculations, one by one. They use a virtual pen on the screen, which I think is helpful if you can actually follow through step by step. So I highly recommend checking that video out. All right, so the next question is, sorry. So possibly, I'm not going to say yes or no. It won't be like 25 generations, but it could be up to like 3 or 4 possibly. All right, there was a question about time lag. So what exactly does time lags and density dependence mean? So what are we just kind of break it apart? What are we talking about when we're talking about time lags in general?
When the density dependence occurs at some time in the past, like not in the present.
Yeah, so relating to density dependence, that's exactly what we're talking about. Can somebody give an example of when we might have a time lag, a lag that causes density dependence? So we think of this terms of maybe reproduction, right? What if we have a really good spring? Do you think reproductive rates might go up or down? If it's a really fruitful like breeding season? Yeah, they might go up, but then say we have a harsh winter and then a really harsh spring the next year. Could that cause an inverse of that effect where we have now really high or low survival rates? So that's kind of the density dependent part, right? So we have, in a good year, we can have high survival rates because they had a lot of resources. But if then they have like a really rough winter followed by a rough spring, that big number that comes into that following spring is going to die off due to that lag effect of having the high numbers. The lag is from the previous high reproductive year, or the previously high reproductive output for the population.
Does that tie with a population that experience like overshoot and also die-offs?
That's another example. Yeah. So if you have, they might overshoot their carrying capacity, or the carrying capacity might go up if resources increase. And then if resources decrease the following year, that carrying capacity potentially goes down. They're going to overshoot the previous carrying capacity or the new carrying capacity. And then that's where the die-off occurs. Yeah, wet seasons or drought could be another example. It could be the opposite of what I said, right? I said there was a really fruitful year followed by a bad year, right? So you could have a really bad year that causes low reproductive rate, so they undershoot carrying capacity, and then the next year is really fruitful and has a lot of resources, so then it kind of elevates and goes really quickly and increases that reproductive season. And that might overshoot, and then then it ties into the oscillations. What causes oscillations, right? Resources is the example that we're talking about right now. That's one thing that causes oscillations, the overshooting and undershooting of carrying capacity. I guess while we're on this, what are the other two reasons, do you remember, that could possibly cause population fluctuations to over and undershoot carrying capacity? Yeah, predators is another one, right? You have the predator-prey cycle. And then very much like, yeah, and then somebody else said parasites. So those are the three main ones that Cogbooks has talked about. Awesome. I guess to re-hit, I found in my notes now, so delayed density dependence, just to be certain, that occurs when the density dependence is based on the population density at some time in the past. And like all the examples we talked about, what causes a population to be a number at a given time could be abiotic factors such as the environment, resources, or biotic factors such as predators or parasites. And then those factors, the predators and parasite numbers, those could change in the future too. So then the population of the prey or the host could also fluctuate and change in the future, depending on where they are in the cycle. I don't believe, no, we have not talked about metapopulations yet today. So why don't we start with the basics of that, and let's just define what is a metapopulation.
It's when species are able to move between patches of subpopulations because of fragmented habitats.
Yeah, exactly. You have a population of organisms, but they're broken up into subpopulations. And as I said, that's typically related to habitat fragmentation. So it could be, you have a couple islands that are fragmented by water. You have ponds in wetlands that are fragmented by dry land. You have forests that are fragmented by mountains or grasslands in between. And then what are the three types of metapopulation models that Cogbooks talked about?
Basic, source sink, and landscape.
Yes, and let's talk about what are they? What is how would we describe a basic metapopulation model? What does it assume?
It assumes that all of the habitat patches are equal in their quality,
Yep.
and that the habitat matrices between the patches are inhospitable in quality.
Exactly, right? So if we have 4 ponds of a wetland with grass in between, we're saying all 4 ponds are equal in quality. What is that? What do we mean when we say they're equal in quality?
Are you meaning like how beneficial they would be to that species living in all 4 of those ponds?
Well, I
Like
mean,
they're the ideal conditions?
not necessarily, I wouldn't say ideal conditions, but in the chat, resources and such, yes, they have the same amount of resources. So they have the same predation levels. They have the same, competition levels. Everything about them is equal. And is that a realistic approach? No, right? We know that things differ. So then what does, how do we build off the basic metapopulation model using a source sink metapopulation model or a landscape metapopulation model? Let's start with the source sink first. What does that add to it that the basic model doesn't have?
Are you talking about the differences between source and sink when it comes to like numbers and disbursement?
Not yet. I was just asking if we're talking about the models themselves of metapopulations, what does the source sink have in the model, or what is an assumption that it is not in the basic? And somebody said, yeah, in the chat, patches vary in quality, right? So the source sink acknowledges that patches are different. What does it not consider? Or we have 2 parts to the model, right? We have the matrix, right? So I was going to say we have to consider what the assumptions are about the patches and what the assumptions are about the matrix in between the patches. And in the basic model, right, we have the patches are equal and the matrix is inhospitable. In the source sink, it has an additional assumption. It acknowledges that the patches are different in quality, but it still has the basic assumption that the matrix is inhospitable, like it keeps it constant. But if we want to talk about the source sink a little bit, what do we mean when we say source and what do we mean when we say sink?
High quality patches are known as sources. And the low quality patches are known as sinks. And it all has to do with the number of individuals it's producing that can be dispersed to other patches.
Yeah, so is a sink population able to sustain on its own?
Not really. It relies on other patches to keep it from going low or going extinct.
Yeah, it relies on source populations, right? From high quality patches, right? The source population can produce more than enough individuals and they can disperse into these lower quality patches or the sink patches and become a sink population where they might be able to live as adults in these low quality patches, but they can't reproduce enough. The quality is not good enough. So if we remove the source population, the sinks would all eventually go extinct. So what about the third one then, the landscape metapopulation model? How would we describe this one?
It describes, or I guess it just states that, both patches and the habitat matrix can vary in quality.
Yeah, exactly, right? So this is the most realistic one where it says, how would we, what could be some examples of high quality versus low quality matrix? What do we mean when we're talking about the quality of the matrix? And remember, what's the matrix used for again? Let's start there. Yeah, moving between patches, exactly. So let's make a hypothetical. We have 4 patches of forest with like open grassland type scrub brush in between. What would make maybe a high quality matrix in between forest? Say we're talking about mice that live in these forests and they want to move between patches, what would be a good quality matrix to help them move across to the other one patch to another?
If there's cover to provide protection.
Yeah, so say there's tall grass or there's a lot of logs or hiding places for them, right? So it's going to lower the probability of them getting seen by a predator versus if one is kind of open dirt, right? They can be seen very readily by aerial predators and it's not very safe. So we maybe consider that a lower quality matrix. All right, are there any more questions about metapopulations or anything else we want to talk about there? Any other topics that we wanted to talk about? So the question is, should we focus on definitions for this test? I would say yes, in general, we should, if they're bolded terms, Cogbooks is pointing out that they're important terms to know, but knowing the definition and being able to regurgitate it is a good start, but I would say being able to talk about it in a few sentences is important too. So a lot of times you might get asked a question like define this, you might expand on that and say compare and contrast it to another definition, especially if you get those multiple definitions in a row like we just talked about with the 3 different metapopulation models. Okay, and if anybody else has questions, we can stand for a little bit longer. If not, we can call it a session too, so you can go back to studying or review some of the topics we went over here.
I have a question, but just for you personally.
Okay, do you want to hang
That's
on
okay.
until after?
Yeah, I can hang out.
Okay, so does anybody else have a question that they want to talk about related to the course or the exam or? I mean, you go beyond memorization, I would say for sure. Like we talked about being able to explain concepts and just trying to link one module to another. So it's gonna they're not all, how do I want to put it? All 5 of the modules that you went through for this exam are related in one way or another. So you might think about additional questions on how some of the topics build into each other versus, or how some of the topics are similar and why we use certain methods or why other why did we learn multiple models? Why did we learn exponential? Why did we learn geometric growth? Why did we learn logistic? And why do we have the matrix tables? Why not just one model for, one size fits all? So think about, why are there different approaches? So conceptually, that might be something good to know. I think somebody put up a Discord page, which I think is a great idea that students do for these courses. If you participate in it, awesome. If not, maybe take a look at that. I think the original link is in our community discussion. Use each other. This course, while it's 100% online, there's 160 some of you in the course right now. So you have each other as resources. I would practice teaching concepts to each other. Teaching is a good way of learning or knowing if you actually understand it. So. All right, so I guess if there's no more questions, this was a good session. I think, we learned some stuff, and your classmates, so appreciate you participating for sure on this. So, no problem. That's what I'm here for. And if somebody does want to talk, so if everybody else wants to log off, that would be appreciated. I'm going to go ahead and stop the recording, and then I will post the video for this in the next half hour, however long it takes to download.